Okay, let's unpack this. We all know about solar power, right? Capturing the sun. But imagine if your solar panels could also make electricity from, well, rain. Our deep dive today takes us to Burlington, Vermont. We're looking into whether these cutting-edge rain-powered solar panels are actually viable for you there.
Yeah, it's really interesting stuff. The core idea here, what makes it innovative, is that they're hybrid systems. They combine the traditional photovoltaic cells, PV, with something new called triboelectric nanogenerators.
Yeah.
TANGs for short.
Payangs, okay.
Exactly. So they grab energy from sunlight and from the kinetic energy of raindrops hitting the panel. It's a pretty fascinating step towards maybe 247 generation, regardless of the weather.
A hybrid system. That's pretty cool. So this triboelectric effect, is it basically static electricity like rubbing a balloon on your head, or is it more complex?
You're definitely on the right track. It is very similar to static electricity at its heart. TNs convert that mechanical impact, the raindrop hitting the surface, into electricity through friction. So when a raindrop hits a special polymer layer, something like PDMS, polydimethylsiloxane, which sits on the solar cell, that friction generates a charge. What's really clever, though, is how they're making the surfaces. They're textured.
Textured? How so?
Well, some researchers have even used patterns, like the grooves from old DVDs, to basically amplify the effect, make it more efficient. They've seen lab results, small scale of course, where a single drop on a dual layer design, think PDMS plus a conductive polymer, can generate, measurable electricity. Around 2.14 volts, maybe 33 nanoamps.
Wow. Okay, not huge amounts yet, but
Yeah.
measurable from a drop.
Exactly. Enough for maybe a tiny sensor. The big question is scaling it up.
Right, scaling. Now, I've also heard graphene mentioned with these. How did that work? Raindrops on graphene. Sounds different.
It is, yeah, it's another angle. Researchers, I believe in China, found that when rain hits electron-rich graphene, it kind of forms a pseudocapacitor, like a tiny battery.
A battery from a raindrop. Sort of. The key is the salts dissolved in the rainwater, even common stuff, ammonium, calcium ions. These ions create gradients that basically push electrons across the graphene, generating a current. It's pretty neat. It holds that promise of maybe round-the-clock generation, rain or shine. But it's still very experimental.
Okay.
Current versions have issues with scaling up, and they actually lose some solar efficiency in bright sun compared to standard panels. Trade-offs.
Trade-offs, always. So, okay, we have these two cool bits of tech tangs and graphene. Let's bring it back to Burlington. How does this lab stuff actually hold up in the real world there? What are the local challenges?
Right, Burlington's reality check. Well, first, it's latitude 44.48 degrees north. That means huge seasonal swings in sunlight. You're looking at potentially a 68% drop in solar power production in winter versus summer. Shorter days, lower sun angle, and crucially, snow cover.
Ah, snow, right.
And while Burlington gets decent rain, about 39 inches a year over maybe 123 days, which sounds good for tens.
Yeah, sounds ideal. The problem is winter precipitation. Snow, ice. TNGs, at least the current ones, basically stop working below freezing, 0 Celsius, unless you actively heat them, which uses energy.
Defeats the purpose a bit.
Kind of does. Plus, other local factors matter. Things like radar blind spots, making rain forecasting tricky, and apparently lower salt content in Burlington's rainwater compared to some other areas.
Lower salinity, which would impact the graphene ones.
Exactly. Less dissolved salts means less potential for that ion gradient effect in the graphene systems.
Okay, so real-world hurdles. Are there any existing solar projects in Burlington that kind of give us clues maybe about resilience or how people are tackling energy locally?
Yeah, definitely. You can look at the Hillside East community. They've got a solar battery microgrid set up using things like Tesla Powerwalls, smart panels. It's a really good model for community resilience, managing their own power.
But they don't have the rain panels yet.
No, not these hybrid ones. Now, you could imagine integrating tangs, maybe enhancing winter reliability, perhaps generating some power even when PV panels are snow-covered. But here's the catch. Current tang output is really low, like 2 to 5 watts per square meter. That's nowhere near enough power to handle big loads like heating the panels to melt snow.
Right, not enough juice. So bringing it all together for you, the listener in Burlington, what are the biggest roadblocks, the practical economic things stopping this from taking off right now?
Well, the economics are tough, these hybrid panels. They're looking at being 30 to 50% more expensive than standard PV panels right now.
Ouch.
And there's that efficiency hit. The transparent tang layer on top reduces the solar cell's performance by, say, 8 to 12% in good sunlight. So you pay more, get slightly less solar power, hoping the rain makes up for it.
Which it might not, especially in winter.
Precisely. Then there's maintenance. keeping them clean, dealing with snow. And the polymer layers in tenjings can degrade over time. They might need more servicing. And we shouldn't underestimate community trust. If panels, even regular ones, were poorly installed in the past and cause issues like roof leaks, people get skeptical.
Rightly so.
Yeah. So you really need clear, honest cost-benefit analysis to cut through any green marketing hype and show if and when this technology actually makes sense for a homeowner or community.
Okay, so it's definitely promising, fascinating science, but clearly facing some big hurdles for real-world use, especially somewhere like Burlington. Where does this leave us? What's the path forward? Is this the next big thing or still very much R&D?
I think the perspective has to be nuanced. Rain-powered solar, TENS, graphene.
Mhm.
It's nascent, it's early days, but it does hold promise for climate resilience down the line,
Mm.
especially if research keeps improving things like low-temperature tan performance or ways to maybe boost that salinity effect for graphene.
So keep watching the research.
Absolutely. But for immediate energy needs, for today and the near future, the priorities probably still lie in improving conventional solar efficiency, deployment, and really expanding battery storage. That addresses the core needs more directly right now.
That makes sense. It really raises an interesting question, though, doesn't it? Even if these aren't mainstream yet, how might these kinds of emerging technologies, these hybrid ideas, start changing how we even think about energy generation in ways we haven't expected?